Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin our journey into the deepest mystery the universe has to offer, take a moment to get comfortable. Let your body settle into whatever space holds you right now. Where in the world are you watching from? A quiet bedroom where the day has finally released its hold? A cozy corner where the night feels gentle and safe? Wherever you are, you're exactly where you need to be. Tonight we're going to explore something remarkable, something that challenges everything we thought we understood about the beginning of everything. We're going to contemplate what might have existed before the Big Bang, that moment we've long considered the origin of time and space itself. We'll discover evidence from the cosmic microwave background, examine theories of cyclic universes and quantum fluctuations, and contemplate the possibility that our universe might be just one chapter in an eternal story. It's a journey that spans not just the observable universe, but the very concept of existence itself. But don't worry. This isn't going to be an anxious exploration of terrifying cosmic mysteries that keep you awake with existential dread. Instead, we'll move slowly and carefully through the science, the mathematics, the observations, and the profound philosophical implications, taking our time with each discovery. By the end, I think you'll find that the mystery of what came before is less frightening than it is deeply, beautifully humbling. If you enjoy these calm explorations of the cosmos, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting me with these quiet hours when the universe feels close. So settle in, let your shoulders drop away from your ears, take a slow breath, and let it out even slower. And let's begin our slow drift through the greatest mystery we can imagine. There's nowhere you need to be right now, nothing you need to solve. Just listen and let the story of what might have come before unfold like starlight reaching us across impossible distances. For nearly a century we've told ourselves a story about the beginning. It's a story that starts with a singularity, an infinitely dense point that contained everything that would ever be, and then, in a moment we call the Big Bang, that point expanded into space and time and matter and energy. It's the story written in textbooks, the narrative that shaped modern cosmology, the answer we give when children ask where everything came from, and for a long time, that story felt complete. The Big Bang theory emerged in the 1920s, when astronomers noticed something peculiar about distant galaxies. They were moving away from us, not just one or two, but all of them, in every direction, as if the entire universe was expanding. If you run that expansion backward in time, everything converges to a single point, a moment roughly 13.8 billion years ago, when the universe as we know it began. The mathematics worked beautifully. The predictions matched observations. Light elements formed in exactly the proportions we see today. The cosmic microwave background radiation, that faint whisper of heat, left over from the early universe, appeared precisely where the theory said it should. But here's the thing about beginnings. The closer you look at them, the stranger they become. When physicists try to understand what happened at the exact moment of the Big Bang, at time equals 0, the equations broke down. They produced infinities, impossibilities, singularities where the laws of physics simply stopped making sense. And that should have been a clue. Not that the Big Bang didn't happen, but that perhaps it wasn't really the beginning at all. Think of it this way. Imagine you're watching a film and someone asks you when the story begins. You might say it begins when the opening credits roll, when the first scene appears on screen. But what about the script that was written before filming? What about the ideas that formed in the writer's mind before the script existed? What about the cultural and historical context that made those ideas possible? The beginning you identify depends entirely on how far back you're willing to look, how deeply you're willing to question what came before the before. For decades, cosmologists treated the Big Bang as an impenetrable wall. Don't ask what came before, they said. because time itself began at that moment. The question was meaningless, like asking what's north of the North Pole. But some scientists couldn't let it go. They saw patterns in the cosmic microwave background, subtle anomalies in the way galaxies distributed themselves, mathematical structures that seemed to hint at something deeper. And slowly, carefully, they began to wonder whether the Big Bang might be less like the beginning of a story and more like the opening of a new chapter. The possibility that something existed before the Big Bang doesn't diminish the event itself. The universe did expand from an incredibly hot, incredibly dense state. Space did stretch, matter did form, stars did ignite. All of that remains true and observable and mathematically rigorous. But what if that moment of expansion wasn't creation from nothing, but transformation from something? What if the Big Bang was a transition, a phase change, a rebirth rather than a birth? And this is where our journey truly begins, at the edge of what we thought we knew, ready to peer into what might lie beyond. The cosmic microwave background is the oldest light we can see. It's radiation that has travelled across the universe for more than 13 billion years, released when the cosmos was just 380,000 years old. Before that moment, the universe was too hot and too dense for light to travel freely. Photons bounced endlessly between particles trapped in an opaque fog. But when the universe cooled enough for atoms to form, light suddenly broke free, rushing outward in all directions. That's the light we detect today. Cooled by cosmic expansion into microwave frequencies, forming a faint glow that fills the entire sky. When scientists first mapped the cosmic microwave background in detail, they expected to find it perfectly smooth, a uniform temperature in every direction. Instead, they discovered tiny variations, temperature differences of only a few millionths of a degree, but variations nonetheless. These ripples became the seeds of everything we see today. Regions that were slightly denser pulled in more matter through gravity, eventually forming galaxies and stars and planets. The pattern of these ripples told cosmologists about the early universe's composition, its geometry, its rate of expansion. But hidden within those ripples were stranger features, anomalies that didn't quite fit the standard model. A cold spot, larger than it should be, sitting in the southern celestial hemisphere. An asymmetry between opposite halves of the sky, as if the universe had a preferred direction. Oscillations in the temperature patterns that seemed to suggest the universe rang like a bell, carrying echoes of something that happened before the Big Bang. These features are subtle. They require incredibly precise measurements and careful statistical analysis. Some scientists argue they might be nothing more than random fluctuations, the cosmic equivalent of seeing patterns in clouds. But others see something more intriguing. They see the possibility that the cosmic microwave background carries imprints from whatever came before. The way a bell's tone depends on how it was struck, or the way ripples on a pond tell you something about the stone that disturbed its surface. One particular feature caught researchers' attention. When they analysed the larger scale patterns in the cosmic microwave background, they found less variation than expected. It's as if something smoothed out the universe on the larger scales, something that happened before our observable universe began its expansion. Some theorists propose that this smoothing came from a previous universe, one that underwent its own expansion and contraction before giving rise to ours. The collapse of that universe would have erased most of its structure, but not all. Some patterns would survive, imprinted on the cosmic microwave background like a watermark. Another possibility emerged from quantum mechanics. At the smallest scales, at the Planck length, where space and time themselves become grainy and uncertain, quantum fluctuations create tiny, random variations in the fabric of reality. These fluctuations existed even before the Big Bang, some theorists suggest. When the universe expanded, these quantum ripples were stretched to cosmic scales, frozen into the pattern we see today. If that's true, then the cosmic microwave background doesn't just show us the early universe. It shows us the quantum foam that existed before time began, the substrate from which everything emerged. The beauty of these observations is that they're not speculation. The cosmic microwave background is real, measurable, testable. Multiple satellites have mapped it with increasing precision. The patterns are there, waiting to be interpreted. What we're uncertain about is the interpretation itself, the story we tell to explain what we see. And that uncertainty isn't a weakness. It's an invitation, a reminder that the universe still holds mysteries we're only beginning to unravel, and perhaps those mysteries stretch back before the beginning we once thought was absolute. At the heart of the Big Bang theory lies a mathematical problem that has troubled physicists for generations. If you follow the equations backward in time, toward the moment of the Big Bang itself, the density of the universe increases without limit. Space shrinks to nothing. Temperature rises to infinity. And when physicists see infinities appear in their equations, they know something has gone wrong. Infinity isn't a number. It's a sign that the mathematics has reached the boundary of its validity, that the equations are trying to describe something beyond their capacity. This problem appears in Einstein's general relativity, the theory that describes gravity as the curvature of space-time. General relativity works beautifully for describing stars and galaxies and the expanding universe. But when you compress all the matter and energy in the universe into an infinitesimally small point, the equations produce what's called a singularity. At a singularity, the curvature of space-time becomes infinite, and the theory breaks down. It's not that the universe actually contained an infinite density. It's that general relativity can't tell us what happened at that moment. The theory is silent precisely when we need it most. Physicists have long suspected that this silence points toward a deeper theory, one that combines general relativity with quantum mechanics. Quantum mechanics describes the behavior of matter and energy at the smallest scales, where particles can exist in multiple states simultaneously, and uncertainty is built into the fabric of reality. General relativity describes the largest scales, where massive objects warp the geometry of space and time. These two theories have never been successfully unified, but most physicists believe that at the extreme conditions of the Big Bang, both quantum effects and gravitational effects would have been crucial. This is where ideas about what came before begin to take mathematical form. If quantum mechanics applies at the moment of the Big Bang, then the singularity might not be a true singularity at all. Quantum effects could prevent the universe from collapsing to a point of infinite density. Instead, there might be a minimum size, a quantum bounce where the universe reaches a smallest possible scale and then rebounds into expansion. If that's the case, then the Big Bang wasn't the beginning. It was the moment of transition between a previous contracting phase and our current expanding phase. Several mathematical frameworks explore this possibility. Loop quantum cosmology, for instance, applies techniques from loop quantum gravity to the early universe. In this approach, space itself is quantized, made up of discrete chunks rather than being infinitely divisible. When you model the universe with this quantum structure, the singularity disappears. The universe can contract to a very small but finite size, and then quantum effects create a repulsive force that drives expansion. The Big Bang becomes a big bounce, and what came before was simply an earlier phase of cosmic evolution. Other approaches use string theory, which proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings. String theory requires extra dimensions beyond the three of space and one of time that we experience. In some versions of string theory, our universe exists on a multi-dimensional membrane, and the Big Bang might have resulted from a collision between our membrane and another. Before the collision, both membranes existed, each carrying their own matter and energy. The collision triggered the expansion we call the Big Bang, but it wasn't a beginning from nothing. It was an interaction between pre-existing structures. What's remarkable about these mathematical explorations is their consistency with observation. They don't contradict what we see in the cosmic microwave background or in the distribution of galaxies. They offer different interpretations of the same evidence, different ways of understanding what the data is telling us. And while we can't yet say which interpretation is correct, the fact that multiple consistent frameworks exist suggests that the question of what came before is not just philosophical, it's a scientific question, one that might eventually have an answer rooted in mathematics and observation, in equations and evidence. There's an old idea, one that appears in various forms across different cultures and philosophies, that time is not a line but a circle. History repeats, endings become beginnings. What dies is reborn. In modern cosmology, this ancient notion has found new expression in theories of cyclic universes, models where the Big Bang is not a unique event but one moment in an endless sequence of expansions and contractions. The basic idea is elegant. Imagine the universe expanding from the Big Bang. As we observe it doing today, galaxies form, stars ignite, planets coalesce. But expansion doesn't continue forever. Eventually some force, perhaps a strange form of energy, woven into the fabric of space itself, causes the expansion to slow, stop, and reverse. The universe begins to contract. Galaxies move closer together. Space shrinks. Matter and energy compress. But instead of collapsing into a singularity, quantum effects create a bounce. The universe reaches a minimum size and then expands again, starting a new cycle. This isn't just philosophical speculation. Physicists have constructed detailed mathematical models of cyclic cosmologies. In some versions, each cycle lasts trillions of years. The universe expands, forms structures, then contracts and rebounds. With each cycle, the universe might be slightly different. The fundamental constants could vary. The amount of matter and energy could change, but the overall pattern repeats, an eternal rhythm of expansion and contraction. Death and rebirth. One particularly intriguing model, developed by physicists Paul Steinhardt and Neil Turok, proposes that our universe undergoes cycles driven by the behaviour of extra dimensions predicted by string theory. In their framework, two three-dimensional membranes exist in a higher dimensional space, separated by a small gap. These membranes are attracted to each other. They slowly drift together over trillions of years. When they collide, the energy of the collision heats the membranes, creating the hot, dense state we observe as the Big Bang. The membranes bounce apart, cool down, and the matter and energy on them forms galaxies and stars. Then, slowly, the membranes drift together again, repeating the cycle. What's beautiful about this model is that it solves several puzzles that have long troubled cosmologists. One puzzle involves the flatness of the universe. Observations show that the geometry of space is remarkably flat, neither curved like a sphere nor curved like a saddle. For the universe to be this flat today, it would have had to be extraordinarily, almost impossibly flat at the moment of the Big Bang. That seems like a remarkable coincidence unless there's some mechanism that drives the universe toward flatness. In cyclic models, each collision between membranes smooths out irregularities, flattening the geometry naturally over many cycles. Another puzzle involves the cosmic microwave background's uniformity. Regions of the sky separated by vast distances have almost exactly the same temperature, even though they couldn't have been in contact since the Big Bang. How did they reach the same temperature? In cyclic models, these regions were in contact during previous cycles. They had time to equilibrate before the current cycle began, which explains the uniformity we observe today. Of course, these models face challenges. Critics point out that entropy, the measure of disorder, should increase with each cycle. Eventually the universe should become too disordered to continue. Proponents respond that if the universe expands enough between cycles, entropy density decreases, allowing the cycles to continue indefinitely. Others question whether quantum effects could really prevent a singularity at the bounce. The mathematics is complex, and definitive answers require a complete theory of quantum gravity that we don't yet have. But even without definitive answers, the idea of cyclic universes offers a compelling possibility. If our Big Bang was preceded by a previous universe, then perhaps that universe was preceded by another, and so on, infinitely into the past. Time didn't begin. It has always been flowing, carrying universes through endless cycles of creation and destruction, and what we think of as the beginning might simply be the moment we can see most clearly, the point beyond which our observations fade into earlier chapters of an eternal story. In the early 1980s, physicist Alan Guth proposed a solution to several cosmological puzzles that has since become a cornerstone of modern cosmology. He called it inflation, a period in the universe's earliest moments when space expanded exponentially fast, growing by a factor of at least 10 to the 26th in a tiny fraction of a second. This rapid expansion solved the flatness problem, explaining why the universe is geometrically flat today. It solved the horizon problem, explaining why distant regions have the same temperature, and it provided a mechanism for generating the tiny density fluctuations that became galaxies. Inflation has been remarkably successful. Its predictions match observations of the cosmic microwave background with stunning precision. But buried within the theory is a question that leads directly to the mystery of what came before. What started inflation? What created the conditions that allowed this exponential expansion to begin? In most models of inflation, the rapid expansion is driven by a field called the inflaton. Think of it as a form of energy filling all of space, sitting at a high energy state. Like a ball perched on top of a hill, the inflaton field is unstable. It wants to roll down to a lower energy state. As it rolls, its energy drives the exponential expansion of space. When it finally reaches the bottom of the hill, inflation ends, and the inflaton's energy converts into matter and radiation, heating the universe and beginning the hot Big Bang phase we observe in the cosmic microwave background. But this raises an obvious question. Where did the inflaton field come from? Why was it sitting at the top of the hill in the first place? Some physicists argue that quantum fluctuations could have created the inflaton field from nothing. A random fluctuation in the quantum vacuum that triggered inflation. Others suggest that the inflaton field might have been left over from a previous phase of the universe, a relic from whatever came before. There's another intriguing possibility. Inflation might not have had a single beginning. Once inflation starts in one region, it can continue eternally in other regions. Imagine the inflaton field rolling down its hill in some places, causing inflation to end and hot Big Bangs to occur. But in other places, the field might remain high, continuing to inflate. And because space is expanding exponentially during inflation, the regions that continue inflating quickly become much larger than the regions where inflation has ended. This creates a scenario called eternal inflation, where Big Bangs are constantly occurring, each one creating a bubble universe, while the inflaton field continues to inflate in the spaces between bubbles. In eternal inflation, our universe, the region we can observe, is just one bubble among an infinite number. Each bubble might have different properties, different physical constants, different amounts of matter and energy. We happen to live in a bubble where the conditions allowed stars and galaxies and life to form. Other bubbles might be very different, perhaps lifeless, perhaps with physics so strange we couldn't recognize them as universes at all. This leads to a profound implication. If inflation is eternal into the future, creating bubble universes forever, then perhaps it's also eternal into the past. Perhaps there was never a first moment when inflation began. It has always been happening, producing universes without end in both directions of time. Our Big Bang wasn't the beginning of everything. It was simply the moment when inflation ended in our particular bubble, allowing our universe to form. The mathematics of eternal inflation is complex and subtle. There are debates about how to calculate probabilities in an infinite multiverse, about whether the theory makes testable predictions. but the core idea is clear and troubling in the best possible way. If inflation is eternal, then the question of what came before the Big Bang has an answer. More inflation, more bubbles, more universes, stretching back infinitely. And the beginning we thought was absolute becomes a local event, important to us but not fundamental to the cosmos as a whole. This possibility invites us to contemplate something even stranger than a singular beginning. And that contemplation will guide us deeper as we continue. One of the most startling ideas to emerge from modern physics is that a universe can, quite literally, come from nothing. Not from empty space, which is actually full of quantum fields and virtual particles, but from true nothingness, the absence of space, time, matter, energy, and even physical laws. This sounds impossible. And in many ways, it violates our everyday intuition about how reality works. But when you take quantum mechanics seriously, when you follow its mathematics into the deepest foundations of existence, this possibility emerges naturally. The key lies in something called quantum tunneling. In the quantum world, particles can do things that would be impossible in classical physics. An electron can pass through a barrier that it doesn't have enough energy to overcome. It doesn't climb over the barrier. It simply appears on the other side as if it tunneled through. This isn't magic. It's a consequence of quantum uncertainty. Particles don't have definite positions until they're measured. Before measurement, they exist in a state of probability, spread out across multiple locations. Sometimes that probability allows them to be on the far side of a barrier, even if classical physics says they shouldn't be able to get there. Cosmologists have applied this same principle to the universe itself. In a framework called quantum cosmology, the universe is treated as a quantum object, subject to the same probabilistic rules as electrons and photons. Just as an electron can tunnel through a barrier, the universe can tunnel into existence from nothing. There's no cause, no trigger. It's a spontaneous quantum event, fluctuating into being from the void. This idea was developed most famously by physicists Alexander Vilenkin and James Hartle and Stephen Hawking, though their approaches differ in important ways. In Vilenkin's model, the universe begins as a tiny quantum bubble, smaller than an atom, fluctuating out of nothingness. This bubble is unstable. Quantum effects cause it to inflate rapidly, growing exponentially until it becomes large enough for classical physics to take over. At that point, inflation ends in some regions, creating big bangs and hot, matter-filled universes like ours. Hartley and Hawking took a different approach. They used a mathematical technique that treats time as if it were another dimension of space in the earliest moments of the universe. In their model, asking what came before the Big Bang's like asking what's north of the North Pole. There is no before, because time itself doesn't exist in the usual sense at the universe's origin. Time emerges gradually as the universe expands, transitioning from a state where it behaves like space into the flowing, directional time we experience. Both approaches lead to universes that begin without a prior cause, that emerge from quantum nothingness through the same kinds of processes that allow particles to tunnel through barriers. This doesn't mean the universe is uncaused in every sense. It's caused by the laws of quantum mechanics, which presumably exist even in the absence of space and time. But it does mean that there might not have been anything before the Big Bang, no previous universe, no pre-existing conditions, just the quantum vacuum and the probabilistic rules that govern it. Critics of these ideas point out several challenges. If the universe came from nothing, where did the laws of quantum mechanics come from? Why do those laws exist rather than others? And if quantum fluctuations can create universes, why aren't we constantly seeing new universes popping into existence around us? Proponents respond that the laws of quantum mechanics might be necessary truths, inherent to the structure of logic itself, requiring no further explanation, and new universes might indeed be forming, but they would be causally disconnected from ours, invisible and unreachable, expanding away into their own regions of space. What's philosophically profound about the universe from nothing is that it suggests existence requires no external creator or initial condition. The universe bootstraps itself into being through quantum processes, emerging from nothingness the way particles emerge from the quantum vacuum. This doesn't answer every question. It doesn't explain why there are laws at all, or why they take the particular form they do. But it does offer an answer to the question of what came before the Big Bang that is simultaneously deeply strange and mathematically rigorous. And perhaps that combination, strangeness and rigour, is exactly what we should expect from the cosmos. When we think of empty space, we imagine a void, a place where nothing exists. But according to quantum field theory, empty space is anything but empty. It seethes with activity, filled with quantum fields that permeate every point in the universe. These fields can fluctuate, creating pairs of virtual particles that spring into existence, exist for a fleeting moment, and then annihilate each other, returning the borrowed energy to the vacuum. These virtual particles. Before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. These virtual particles aren't just theoretical constructs. They have measurable effects. They alter the energy levels of atoms in ways that have been confirmed experimentally with extraordinary precision. They create a force called the Casimir effect, where two metal plates placed close together in a vacuum experience an attractive force because the space between them excludes certain wavelengths of virtual particles. The vacuum is real, and it's anything but empty. This quantum vacuum existed before the Big Bang, or rather it's the substrate from which the Big Bang might have emerged. In quantum field theory, all particles are excitations of underlying fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. What we call matter and energy are ripples in these fields, waves rising above the baseline hum of the quantum vacuum. If the Big Bang was a quantum event, as many cosmologists believe, then it might have been a particularly dramatic excitation of these fields. Imagine the quantum vacuum fluctuating wildly in the earliest moments, creating regions of higher and lower energy. In most regions, these fluctuations cancel out quickly, returning to the vacuum state. But in one region, a fluctuation grew instead of disappearing. Energy concentrated, space began to expand, and that expanding region became our universe. This picture suggests that what came before the Big Bang was the quantum vacuum itself, eternal and unchanging in some respects, constantly fluctuating in others. Our universe didn't emerge from a previous classical universe or from a moment of divine creation. It emerged from the probabilistic, fluctuating nature of quantum reality, a reality that might have no beginning and no end, just an eternal present in which fluctuations rise and fall. But here's where it gets even stranger. The quantum vacuum isn't just one thing. Different configurations of quantum fields can create different vacuum states, each with its own properties. In string theory, there might be an enormous number of possible vacuum states, perhaps 10 to the 500 or more, each corresponding to a different way the extra dimensions could be curled up, each giving rise to different physical laws and constants. This vast collection of possibilities is sometimes called the landscape. If multiple vacuum states exist, then our universe might have started in one state and transitioned to another. Before the Big Bang, the vacuum might have been in a high-energy state, unstable and ready to decay. The Big Bang could have been the moment of transition, when the vacuum decayed to a lower energy state, releasing energy that drove inflation and created the hot, dense conditions we observe. In this scenario, what came before was simply a different configuration of the quantum vacuum, one with different properties than the vacuum we inhabit now. Some physicists go further and suggests that all possible vacuum states are realized somewhere in a vast multiverse. Each vacuum state creates its own bubble universe with its own physical laws. Our universe is just one bubble among countless others, separated by regions of inflating space. The quantum vacuum, in this view, is constantly creating new universes, not through any external cause but through its own inherent quantum nature. This raises profound questions about the nature of existence itself. If the quantum vacuum is eternal and constantly producing universes, then what came before our Big Bang was simply more of the same. Vacuum fluctuations, bubble formations, cosmic diversity. Time might not have a beginning in any global sense, even if our particular universe has a definite starting point. And the question of why there is something rather than nothing might have a surprisingly simple answer. Because the quantum vacuum, with all its fluctuating fields and probabilistic behaviour, is the natural state of reality, requiring no cause or creator, existing simply because nothingness is unstable. One of the deepest puzzles about the Big Bang is the nature of time itself. We experience time as flowing from past to future, a river carrying us from moments that have been to moments yet to come. But time wasn't always this way. In the earliest moments of the universe, under the extreme conditions near the Big Bang, time might have behaved very differently. It might not have flowed at all. It might have been indistinguishable from space, or it might not have existed in any recognizable form. This idea emerges from the intersection of quantum mechanics and general relativity. In general relativity, time is part of space-time, a four-dimensional fabric that can curve and flex in the presence of matter and energy. Near a black hole, for instance, time slows down relative to distant observers. At the event horizon, time appears to stop altogether from the outside perspective. Inside the black hole, space and time swap roles, with time becoming a direction in space. In the quantum realm, time is even stranger. Quantum mechanics describes systems in terms of probabilities that evolve according to specific rules. But those rules assume time as an external parameter, a backdrop against which quantum events unfold. When you try to apply quantum mechanics to the universe as a whole, including space-time itself, you lose that external parameter. Time becomes part of the system you're trying to describe, and the question of what time means becomes deeply unclear. One approach to this problem, developed by Bryce DeWitt and others, leads to something called the Wheeler-DeWitt equation. This equation describes the quantum state of the entire universe, but remarkably, it contains no explicit time variable. The universe, from this perspective, simply is. It exists in a timeless quantum state, a superposition of all possible configurations of matter and space-time. What we experience as time is an emergent property, arising from the particular way we, as observers embedded within the universe, perceive the quantum state. If time is emergent rather than fundamental, then asking what came before the Big Bang might be asking the wrong question. Before implies time, a sequence of moments ordered from earlier to later. But if time didn't exist in the earliest moments, if it emerged gradually as the universe expanded and cooled, then there might be no meaningful _quote _1_ at all. The Big Bang wouldn't be the first moment in a sequence. It would be the boundary where time begins, the point where the timeless quantum state transitions into the flowing time we experience. Stephen Hawking explored this idea using a mathematical technique called Euclidean quantum gravity. In this approach, you temporarily treat time as if it were an imaginary number, which allows you to perform certain calculations that are otherwise intractable. When you do this, the distinction between time and space disappears. The universe becomes a four-dimensional shape with no boundary, no edge, no beginning. Asking what came before is like asking what's north of the North Pole. The question assumes direction, a beyond that doesn't exist. When you translate back from imaginary time to real time, the universe appears to have a beginning, the Big Bang. But this beginning isn't a moment that was preceded by another moment. It's the point where the concept of time itself comes into being. Before that point, or rather in the region of the four-dimensional shape that corresponds to before, time doesn't exist as a flowing dimension. It's just another direction in space. This is profoundly difficult to visualize because our brains evolved to navigate a world with 3 dimensions of space and 1 of time, flowing inexorably forward. Imagining a region where time doesn't flow, where past and future lose their meaning, is almost impossible. But the mathematics suggest it's real, or at least it's a valid way of describing the quantum state of the universe at its origin. If time emerged at the Big Bang, then perhaps what came before wasn't a previous time at all. It was a timeless quantum state, a configuration of probability and potential from which time crystallized as the universe expanded. This doesn't answer every question. It doesn't tell us why that particular quantum state existed or what determined its properties. But it does offer a way of thinking about origins that sidesteps the infinite regress of causes and effects, suggesting instead that the universe's beginning is the beginning of causality itself, the moment when time and sequence and before and after first became meaningful concepts. We've explored the possibility that the Big Bang wasn't a true beginning but a transition, a bounce from a previous contracting phase. This idea has a long history, but it gained new mathematical rigor with the development of loop quantum cosmology, an approach that applies techniques from loop quantum gravity to the early universe. In classical general relativity, when the universe contracts, it eventually reaches a singularity, a point of infinite density where the equations break down. But in loop quantum cosmology, space is not infinitely divisible. At the smaller scales, space comes in discrete chunks, quantized units that can't be subdivided further. When you model the universe's contraction with this quantum structure, something remarkable happens. The contraction doesn't lead to a singularity. Instead, as the universe shrinks to the Planck scale, about 10 to the minus 35 meters, quantum effects create a repulsive force. This force stops the contraction and drives the universe into expansion. The singularity is replaced by a bounce. This isn't just a philosophical preference for avoiding infinities. It's a prediction that emerges from the mathematics when you take quantum mechanics seriously at the smaller scales. And it has testable consequences. A bouncing universe would leave imprints in the cosmic microwave background, subtle patterns in the distribution of temperature fluctuations. Current observations don't definitively confirm or rule out these patterns, but future experiments with more sensitive instruments might be able to detect them. If the universe did bounce, what was it like before the bounce? In the simplest models, it was remarkably similar to our current universe, just running in reverse. Galaxies were moving together instead of apart. Stars were forming from collapsing gas clouds just as they do now. Planets orbited their suns. Life might even have existed. Experiencing time flowing in what we would consider the opposite direction. This raises fascinating questions about the arrow of time, the fact that time seems to flow in one direction, from past to future. In our universe, entropy increases. Systems become more disordered. Eggs break but don't spontaneously reassemble. Heat flows from hot to cold, not the reverse. This directionality is closely tied to the expansion of the universe. As space expands, there's more room for disorder to increase, more configurations that matter and energy can take. If the universe was contracting before the bounce, entropy would have been decreasing, at least from our perspective. But from the perspective of observers in that contracting phase, time would have flowed forward just as it does for us. They would see entropy increasing in their direction of time, even though we, looking back, would see it decreasing. This suggests that the arrow of time is not fundamental but emergent, tied to the expansion or contraction of space. Another possibility is that the pre-bounce universe was not just a time-reversed version of ours, but something genuinely different. Perhaps it had different physical constants, different amounts of matter and dark energy. Perhaps the bounce involved a change in the fundamental laws, a transition from one set of physical principles to another. In this case, what came before would be more alien, harder to understand from our perspective because the rules governing reality were different. Some models suggest that the universe has bounced many times, each bounce potentially resetting or altering the conditions. With each cycle, information from the previous universe might be partially erased, making it increasingly difficult to reconstruct what came before. We might be in the 100th or millionth cycle, with no way to access information about the earlier cycles, because the bounces have scrambled the evidence beyond recognition. The bounce scenario offers a tantalizing answer to the question of what came before. Another universe, similar or different, that contracted to a minimum size and then rebounded into our current expansion. This doesn't push the question back infinitely. It replaces the idea of a singular beginning with a cyclical process that might have no beginning at all, just an eternal rhythm of expansion and contraction, each cycle giving rise to a universe that lives and evolves before collapsing and rebounding into the next. Whether the universe bounced or began from a quantum fluctuation, or emerged from some other process we haven't yet imagined, the mathematics and observations are slowly converging on answers. We're living in a remarkable time when these questions, once purely philosophical, are becoming scientific, testable, subject to evidence and reason. And that transition from speculation to science is one of the most exciting developments in our long attempt to understand where we came from. Every theory about what came before the Big Bang faces a fundamental challenge: the problem of initial conditions. To explain the universe we observe, you need to start with particular configurations of matter, energy, and space-time. But where did those configurations come from? Why did the universe start in a state that would lead to galaxies and stars and planets, rather than some other outcome? This problem is especially acute in the standard Big Bang model. For the universe to end up as flat as we observe it today, it would have had to be extraordinarily flat at the beginning. For regions of space separated by vast distances to have the same temperature, they would have needed to be in thermal contact at some earlier time. For the density fluctuations that became galaxies to have the particular distribution we see, they would have needed specific initial conditions. Inflation was invented partly to solve these problems. By expanding the universe exponentially, inflation takes a tiny region that was in thermal equilibrium and stretches it to encompass our entire observable universe. Any initial curvature gets flattened out by the expansion. Quantum fluctuations during inflation create the density variations that become galaxies. Inflation makes the current state of the universe much less sensitive to the initial conditions before inflation began. But inflation doesn't eliminate the problem, it just pushes it back. You still need to explain why the inflating field started in the right state to drive inflation. If it started at too low an energy, inflation wouldn't happen. If it started rolling too fast, inflation would end too quickly. The range of initial conditions that lead to successful inflation is relatively narrow, which suggests that something selected or created those conditions. Some physicists argue that if inflation is eternal, the problem of initial conditions disappears. In eternal inflation, all possible initial conditions are realized somewhere in the infinite expanse of inflating space. We find ourselves in a region where the conditions were right for inflation to end and create a habitable universe, simply because those are the only regions where observers like us could exist. This is a version of the anthropic principle. The universe appears fine-tuned for life, not because it was designed, but because we can only observe universes capable of producing observers. Other approaches try to derive the initial conditions from deeper principles. In quantum cosmology, the initial state of the universe might be determined by a wave function that describes the probability of different configurations. The Hartle-Hawking no-boundary proposal, for instance, suggests that the universe's wave function is unique, determined by the requirement that space-time be smooth and finite. If true, the initial conditions aren't arbitrary. They're the only conditions consistent with the universe having no boundary in time. loop quantum cosmology offers another perspective. If the Big Bang was a bounce, the initial conditions for our expansion are the final conditions of the previous contraction. This doesn't eliminate the problem entirely because you can still ask about the initial conditions of the first contraction, assuming there was one. But if the bounces continue infinitely into the past, there might be no first cycle, no ultimate set of initial conditions to explain. The universe has always been evolving, and the conditions we observe are just the latest in an eternal sequence. There's also the possibility that the initial conditions were genuinely random, a quantum fluctuation with no deeper explanation. This is unsatisfying to many physicists who prefer to believe that everything has a reason. But quantum mechanics teaches us that some events are truly random, not determined by prior causes. If the universe began as a quantum fluctuation, its initial conditions might simply be a matter of chance. One possibility among many that happen to be realized. What makes the problem of initial conditions so challenging is that it sits at the boundary between physics and philosophy. Physics can tell us how the universe evolved from a given starting point, but explaining why that particular starting point existed seems to require stepping outside the system, invoking something beyond physics itself. Some argue that this quote, _3_ is a multiverse, where all possible initial conditions are realized. Others invoke a creator or fundamental principle that selects one set of conditions over others. Still others accept that some questions might not have answers, that the universe's initial conditions are simply brute facts, unexplainable but real. As we contemplate these possibilities, it's worth remembering that the problem of initial conditions isn't unique to cosmology. Every scientific theory takes certain things as given. Chemistry assumes the existence of atoms and the laws governing their interactions. Biology assumes the laws of chemistry and physics. Physics itself assumes mathematical laws and symmetries. At some level, every explanation rests on assumptions that are not themselves explained. The question is whether the initial conditions of the universe are like these foundational assumptions, basic facts that require no further justification, or whether they point toward an even deeper layer of reality waiting to be discovered. The idea of a multiverse has moved from science fiction to serious scientific discussion over the past few decades. Not everyone agrees that other universes exist, and not everyone agrees on what multiverse even means. But several independent lines of theoretical reasoning point toward the same unsettling conclusion. Our universe might be just one among many, perhaps infinitely many, each with its own properties and history. We've already touched on one version of the multiverse, the one that emerges from eternal inflation. In that picture, our Big Bang was a local event, the end of inflation in one bubble of space. But inflation continues in other regions, creating new bubbles constantly. Each bubble is a universe unto itself, causally disconnected from the others, expanding and evolving independently. The space between bubbles continues to inflate, keeping them forever separate. This isn't the only way to get a multiverse. String theory, the attempt to unify all forces and particles in a single framework, requires extra dimensions beyond the familiar 3 of space and 1 of time. These extra dimensions could be curled up in many different ways, and each way of curling them produces a different set of physical laws and constants. If all these possibilities are realized somewhere, you get a landscape of universes, each with its own version of physics. Then there's the quantum multiverse, which emerges from the many worlds interpretation of quantum mechanics. In standard quantum mechanics, when you measure a particle, its wave function collapses and it takes on a definite state. But the many worlds interpretation says the wave function never collapses. Instead, every possible outcome of a measurement actually occurs, each in a different branch of reality. When you measure a particle's position, the universe splits into multiple copies, one for each possible position. You perceive only one outcome because you're in one branch, but all the others exist just as really. If the many worlds interpretation is correct, then the universe is constantly splitting into incomprehensibly vast numbers of branches, one for every quantum event. Most of these branches are nearly identical to ours, differing only in the positions of a few atoms, but some branches diverge more dramatically. In some, you made different choices. In others, historical events unfolded differently. In others still, quantum fluctuations in the early universe created different arrangements of galaxies, perhaps even different values for fundamental constants, if those constants are determined by quantum processes. The multiverse idea is controversial because it seems untestable. By definition, other universes are causally disconnected from ours. We can't observe them, visit them, or communicate with them. How can we claim they exist if there's no way to gather evidence? Some physicists argue that the multiverse is a consequence of well-tested theories like quantum mechanics and inflation. If those theories are correct in the regimes where we can test them, and if they predict a multiverse when extrapolated, then we have indirect evidence for the multiverse's existence. Others argue that the multiverse is a failure of imagination, a way of giving up on finding deeper explanations. Instead of explaining why our universe has the properties it does, multiverse theories say that all possible properties are realized somewhere, and we happen to find ourselves in a universe with the right properties for life. This feels like cheating to critics, a way of avoiding the hard work of finding fundamental principles that determine the laws of physics. But consider what a multiverse implies for the question of what came before the Big Bang. If our universe is one bubble in an internally inflating multiverse, then what came before was simply other bubbles, other universes, forming and expanding in the inflating space. The Big Bang wasn't a unique cosmic event. It was one instance of a process that happens constantly, throughout an infinite expanse of space. If the many worlds interpretation is correct, then every quantum fluctuation in the early universe created branches where the fluctuation resolved differently. Before our Big Bang, in some sense, there were all the possible ways the quantum state could have evolved, each realized in a different branch. Our universe is one path through an infinitely branching tree of possibilities. The multiverse offers a radical answer to the question of origins. Instead of one beginning, there are countless beginnings, each giving rise to a different universe. Instead of special initial conditions that require explanation, there are all possible initial conditions, realized somewhere in the vast ensemble. And instead of asking why our universe exists, we can ask why we find ourselves in this particular universe rather than another, a question that might have an anthropic answer. We're here because this universe's properties allow for observers like us. The multiverse is humbling. It takes Earth, already demoted from the centre of the solar system, the galaxy and the universe, and demotes it further to one planet in one universe among infinitely many. But it's also strangely comforting. If all possibilities are realised somewhere, then the universe is richer and stranger than we ever imagined, and our existence, far from being improbable, is inevitable somewhere in the infinite expanse of possibilities. There's a peculiar idea that connects black holes to the origin of universes, suggesting that what came before our Big Bang might have been the interior of a black hole in a parent universe. This isn't science fiction, though it sounds like it. It's a serious hypothesis proposed by physicists exploring the quantum mechanics of black holes and the geometry of space-time. A black hole forms when a massive star collapses under its own gravity, compressing matter into an infinitely dense point called a singularity. Around this singularity is an event horizon, a boundary beyond which nothing, not even light, can escape. From the outside, a black hole appears as a dark region of space that swallows anything crossing its event horizon. But what happens inside? What does space-time look like beyond the point of no return? Einstein's general relativity predicts a singularity at the black hole's centre, a point where curvature becomes infinite and the equations break down. But just as the Big Bang singularity might be avoided by quantum effects, the same might be true for black hole singularities. If you apply quantum mechanics to the collapsing matter inside a black hole, something unexpected might happen. Instead of collapsing to a point, the matter might reach a minimum density and then rebound, just as the universe might have bounced at the Big Bang. This rebound could create a new region of space-time expanding like our universe, but disconnected from the parent universe that contained the original black hole. From the outside, the black hole would look normal, swallowing matter and growing. But from the inside, the rebounding matter would create an expanding universe, potentially giving rise to galaxies, stars, and planets. This new universe would be causally disconnected from its parent. Nothing that happens inside could affect the parent universe, and nothing from the parent universe could enter after the bounce occurred. Physicist Lee Smolin developed this idea into a theory called cosmological natural selection. In his model, every black hole creates a new universe. The physical constants in the new universe are slightly different from those in the parent, randomly varied by quantum effects during the bounce. Universes that produce many black holes will have many offspring universes. Over time, the multiverse evolves toward universes whose constants favour black hole formation. This is natural selection applied to universes. Just as organisms with traits that enhance reproduction become more common over generations, universes with constants that favour black hole formation become more common in the multiverse. Our universe produces black holes, which suggests we might be descended from a long line of universes optimised for black hole production. The constants of physics might not be arbitrary or fine-tuned by an external designer. They might be the result of evolutionary processes occurring at the cosmic scale. If this picture is correct, then what came before our Big Bang was the interior of a black hole in a parent universe. That parent universe existed before ours. With its own galaxies and stars and black holes, one of those black holes underwent a quantum bounce, and the expanding region created by that bounce became our universe. We're living inside a black hole, though we'd never know it from the inside. The event horizon that separates us from the parent universe looks to us like the Big Bang, the moment when our region of space-time began expanding. This raises dizzying questions about the chain of creation. If our universe formed inside a black hole, then the parent universe might have formed inside a black hole in a grandparent universe, and that grandparent universe might have formed in a great-grandparent universe. The chain could extend infinitely into the past, with no ultimate origin. Just an endless sequence of universes giving birth to other universes through black hole formation. Critics point out that this idea makes few testable predictions. We can't observe the parent universe or confirm that we're inside a black hole. The theory relies on speculative quantum gravity, which we don't fully understand. But it offers an elegant explanation for why the constants of physics seem fine-tuned for complexity. They're not fine-tuned by design. They're the result of evolutionary processes favouring universes that produce black holes, which happen to overlap significantly with universes that produce stars, planets, and life. There's something poetic about the idea that black holes, objects we often think of as destructive and final, might be seeds of creation, giving birth to new universes. It transforms the cosmos into a living, reproducing entity, constantly creating new realms of existence. And it suggests that the answer to what came before is both simple and profound. Another universe, similar but different, which gave birth to ours through processes we're only beginning to understand. One of the strangest ideas to emerge from theoretical physics in recent decades is the holographic principle, the notion that the entire universe might be a projection from information encoded on a distant boundary. This sounds like the stuff of philosophy or mysticism, but it comes from rigorous mathematical work on black holes and quantum gravity, and it suggests that what we think of as three-dimensional space might actually be something fundamentally different. The story begins with black holes and entropy. In the 1970s, physicist Jacob Bekenstein realized that black holes have entropy, a measure of disorder or information content. Surprisingly, this entropy is proportional not to the black hole's volume, but to the area of its event horizon. A black hole twice as massive has 4 times the surface area and 4 times the entropy. This was unexpected. In ordinary matter, entropy is proportional to volume. A box twice as large holds twice as many particles and has twice as much entropy, but black holes don't follow this rule. Stephen Hawking expanded on this work, showing that black holes emit radiation due to quantum effects near the event horizon. This radiation carries energy, causing the black hole to slowly evaporate. If the black hole evaporates completely, what happens to the information that fell into it? Quantum mechanics says information can't be destroyed, but Hawking's calculation suggested it was lost when the black hole disappeared. This apparent contradiction, known as the black hole information paradox, troubled physicists for decades. The holographic principle emerged as a potential solution. If all the information about what fell into a black hole is encoded on its event horizon, then as the black hole evaporates, the information can be released in the Hawking radiation. The black hole's interior, its volume, is in some sense secondary. The fundamental information is on the surface. Physicists Leonard Susskind and Gerard 't Hooft generalized this idea, suggesting that the same principle might apply to the entire universe. Perhaps all the information in three-dimensional space is encoded on a two-dimensional boundary at the edge of space. Our experience of living in 3 dimensions would be a kind of hologram, a projection from this boundary. The universe wouldn't really have depth in the way we perceive it. Depth would be an emergent property, arising from information encoded on a surface. This idea gained support from string theory, particularly a framework called the ADS/CFT correspondence, developed by Juan Maldacena. This correspondence establishes a precise mathematical relationship between a theory of gravity in a higher dimensional space and a theory without gravity in one fewer dimension. The gravitational theory describes things happening in the bulk, the interior of space. The non-gravitational theory describes things happening on the boundary. Remarkably, these two descriptions are exactly equivalent. Everything in the bulk can be computed from information on the boundary. What does this have to do with what came before the Big Bang? If the universe is holographic, then the three-dimensional space we inhabit might not be fundamental. The fundamental reality might be the information on a boundary, and what we perceive as the Big Bang might be a feature of the holographic projection, not a fundamental event in the underlying description. In some holographic models, time itself is emergent, arising from correlations in the boundary information. If time is emergent, then asking what came before the Big Bang is asking about the behavior of the boundary theory at earlier values of the emergent time parameter. The answer might not involve another physical space or earlier universe. It might involve different configurations of information on the boundary. Configurations that give rise to what we interpret as the pre-Big Bang state. This is deeply abstract and difficult to visualize because it challenges our intuitive understanding of space and time. But the mathematics is rigorous, and the holographic principle has passed numerous consistency checks. If it's correct, then the universe is fundamentally different from what it appears. We're not living in three-dimensional space that emerged from a Big Bang singularity. We're living in a holographic projection from information encoded elsewhere, and the Big Bang might be a feature of how that projection unfolds, not the absolute beginning of reality. Some physicists speculate that the holographic principle could help resolve the singularity problem. If the Big Bang singularity is a feature of the three-dimensional description but not the boundary description, then it might not be a true singularity at all. The boundary theory might be perfectly smooth and non-singular, with the apparent singularity arising only when we project that information into three-dimensional space. In this view, what came before the Big Bang is simply earlier states of the boundary information, states that didn't yet project into the expanding three-dimensional universe we observe. The holographic principle is still speculative, and many questions remain unanswered. We don't know if our universe is truly holographic or what the boundary would be, but the principle offers a radically different perspective on the nature of space, time, and the Big Bang. It suggests that the answers we're seeking might not lie in the history of three-dimensional space, but in the structure of information encoded in a fundamentally different description of reality. We experience time as flowing in one direction, from past to future. Memories form of events that happened, not events that will happen. Eggs break but don't spontaneously reassemble. Heat flows from hot to cold. This asymmetry, the arrow of time, seems fundamental to our existence. But the laws of physics don't inherently prefer one direction of time over another. They're time symmetric. The equations work equally well running forward or backward. So why does time seem to flow in only one direction? The answer, physicists believe, lies in entropy, the measure of disorder. The second law of thermodynamics states that entropy increases over time in isolated systems. A broken egg has higher entropy than an intact egg because there are more ways for the egg to be broken than to be assembled. Heat spreading out has higher entropy than heat concentrated in one place. The increase of entropy creates the arrow of time. We remember the past because it had lower entropy than the present, which had lower entropy than the future. But why did the universe start with low entropy? The Big Bang began in an extraordinarily low entropy state, with matter and energy distributed nearly uniformly, just slightly clumpy enough to eventually form galaxies. If the initial state had been high entropy, the universe would have been a featureless, maximally disordered soup, and no structures would have formed. The fact that we exist at all is evidence that the Big Bang started with low entropy. This raises the question, what if the universe before the Big Bang had even lower entropy? Or what if time ran backward before the Big Bang, making what we call before actually after, from a different perspective? Some cosmological models explore this possibility, imagining a universe that expands from the Big Bang in both directions of time, with entropy increasing in both directions away from the Big Bang. In this picture, the Big Bang is not the beginning of time but the moment of minimum entropy. Time extends infinitely in both directions from this point, but in both directions entropy increases. Observers on either side would perceive time flowing away from the Big Bang, experiencing their direction as forward and the other as backward. From our perspective, the Big Bang is in the past and time flows toward the future. But from the perspective of observers on the other side, the Big Bang is also in their past, and time flows in what we would consider the backward direction. This model solves the problem of why the Big Bang started with low entropy. It didn't start at all. It was simply the lowest entropy point in an eternal timeline. But it creates new puzzles. What would the universe look like on the other side of the Big Bang? Would it have the same physical laws? Would there be galaxies and stars or something entirely different? And how would the two sides be connected? If time runs in opposite directions, can they influence each other? Or are they completely independent? Some versions of this idea propose that the two sides are mirror images, with matter on one side corresponding to antimatter on the other. In our universe, matter dominates over antimatter. Perhaps on the other side, antimatter dominates. The asymmetry we observe would be balanced by an opposite asymmetry on the far side of the Big Bang, preserving symmetry at the cosmic scale while breaking it locally. Another possibility is that time doesn't run smoothly backward before the Big Bang, but instead becomes scrambled or undefined. Near the Big Bang, under extreme quantum conditions, time might not have a clear direction. It might fluctuate, sometimes flowing forward, sometimes backward, sometimes not flowing at all in any recognizable sense. Only as the universe expanded and entropy increased would time crystallize into the flowing, directional experience we have. The idea of time running backward challenges our intuition, but is not impossible. The laws of physics allow it. What prevents it in everyday life is the initial condition of low entropy at the Big Bang. If that condition is explained by a symmetric model, where entropy increases in both temporal directions, then backward flowing time becomes a natural consequence rather than a paradox. Thinking about time this way changes how we understand the question of what came before. If time ran backward before the Big Bang, then quote 7 is a misleading word. What we're really asking about is another branch of time, another region of the universe where entropy increases in the opposite direction. And the answer to what's there might be surprisingly familiar. Another expanding universe, filled with matter and energy, evolving and creating complexity, just as ours does, but flowing in the opposite temporal direction. There's one more possibility to consider, one that's less about physics and more about philosophy, but which has gained surprising traction in recent years. What if our universe isn't fundamental at all? What if it's a simulation, created by some advanced civilization in apparent reality? In that case, what came before the Big Bang was the decision to run the simulation, the activation of the computational substrate that generates our reality. This idea, popularized by philosopher Nick Bostrom, rests on a simple argument. If it's possible to create sufficiently detailed simulations of universes, and if advanced civilizations are likely to create such simulations, then there could be far more simulated universes than real ones. If you assume you're a typical observer, you're statistically more likely to be in a simulation than in base reality. The argument has several assumptions. First, it must be possible to simulate a universe in sufficient detail that conscious observers within the simulation can't tell they're simulated. This is far beyond our current technology, but it's not obviously impossible. Our computers already simulate simple physical systems. In principle, with enough computational power, you could simulate atoms, molecules, chemistry, biology, and eventually conscious beings. Second, advanced civilizations must be willing to run such simulations. Perhaps they do it for scientific research, to study how universes evolve. Perhaps they do it for entertainment, creating worlds to observe and interact with. Perhaps they do it for reasons we can't fathom. But if even a small fraction of advanced civilizations run simulations, and each civilization runs many simulations, the number of simulated universes quickly dwarfs the number of real ones. Third, you have to assume you're a typical observer, equally likely to be in a simulation as in base reality. This assumption is controversial. Some argue that observers in simulations might be less conscious, or less real than observers in base reality, making the assumption invalid. If we are in a simulation, then the Big Bang wasn't a physical event. It was the initialization of the simulation, the moment when the program started running. What came before was the parent reality, where the simulation is running. That reality might have very different physics, different dimensions, different laws. It might not even be physical in the way we understand it. The creators might exist in a realm where consciousness is fundamental and matter is derived, or where time doesn't flow, or where causality works differently. From our perspective, we could never detect the simulation directly. If it's sufficiently detailed, it would be indistinguishable from a real universe. We'd perceive physical laws, matter, energy, space and time all behaving consistently. But that consistency would be a feature of the program, not evidence that we're in base reality. Some have proposed ways to test the simulation hypothesis. If the universe is simulated on a discrete computational substrate, there might be limits to precision or resolution. Perhaps there's a smallest unit of space or time, a kind of pixelation that could be detected in high-energy physics experiments. Perhaps there are computational shortcuts, places where the simulation approximates rather than exactly computing outcomes, which could show up as anomalies in our observations. But these tests are speculative. A sufficiently advanced simulation might have no detectable limits within the observable universe, or the creators might intentionally design the simulation to be undetectable, ensuring that observers within can never confirm they're simulated. The simulation hypothesis is troubling to some because it seems unfalsifiable. If we can't detect whether we're in a simulation, how is it different from any other metaphysical claim? But others argue that unfalsifiability doesn't make an idea useless. The simulation hypothesis changes how we think about existence, origins, and purpose. If we're in a simulation, then the ultimate questions about the universe aren't about the Big Bang or quantum mechanics. They're about the creators and their motivations. What came before the Big Bang in this view is the act of creation itself, the moment when some intelligence in apparent reality decided to run a simulation and set its initial parameters. Our universe's physical constants, its initial conditions, the laws that govern it, all these would be design choices, made for purposes we can only guess. This idea is profoundly humbling and profoundly strange. It takes the question of origins out of the realm of physics and into the realm of metaphysics and theology. But it's also a reminder that the question of what came before the Big Bang might not have a physical answer. The universe might be embedded in a larger reality that doesn't follow the rules we've discovered through science. And if that's the case, then the search for what came before might lead us not to earlier moments in time, but to entirely different categories of existence that we're only beginning to imagine. This is perhaps the deepest question we can ask, deeper even than what came before the Big Bang. Why does anything exist at all? Why is there a universe, or a multiverse, or a quantum vacuum, or laws of physics, rather than absolute nothingness? This question has haunted philosophers for millennia, and it remains fundamentally mysterious even in the age of modern science. One approach is to argue that nothingness is unstable. In quantum mechanics, the vacuum is not empty, but filled with fields that can fluctuate. These fluctuations can create particle-antiparticle pairs that briefly exist before annihilating. If the vacuum is inherently unstable, if fluctuations are inevitable, then perhaps the question answers itself. There is something rather than nothing, because nothing is impossible. The quantum vacuum, with all its fields and fluctuations, is the natural state, and universes emerge from it through processes we've described. But this answer raises another question. Why do the laws of quantum mechanics exist? Why those laws and not others, or no laws at all? You've pushed the mystery back one level, from the existence of the universe to the existence of physical laws. Some physicists argue that the laws of quantum mechanics might be necessary truths, inherent to the structure of logic and mathematics. Just as 2 plus 2 necessarily equals 4, the laws governing quantum fields might necessarily follow from deeper principles. This leads to a view called mathematical Platonism, the idea that mathematical structures exist independently of physical reality. In this view, all possible mathematical structures exist in some abstract sense, and physical universes are particular mathematical structures that happen to contain observers. Our universe exists because the mathematical structure that describes it exists, and that structure exists because all mathematical structures exist, requiring no further explanation. Physicist Max Tegmark has developed this idea into what he calls the mathematical universe hypothesis. He argues that physical reality is not just described by mathematics, but is mathematics. When we discover mathematical laws governing the universe, we're not finding approximate descriptions of something deeper. We're finding the actual structure of reality. The universe is a mathematical object, and it exists in the same sense that all mathematical objects exist. If this is true, then the question of why there is something rather than nothing dissolves. There isn't a physical something that was created from nothing. There's a mathematical structure that exists necessarily, the way the Mandelbrot set, or the number pi exists. Asking why it exists is like asking why 2 plus 2 equals 4. It's not a contingent fact that could have been otherwise. It's a necessary truth. But not everyone finds this satisfying. Critics argue that mathematical structures are abstract, not physical. They don't weigh anything, don't occupy space, don't have causal power. Saying the universe is a mathematical structure doesn't explain why we have the subjective experience of existing within that structure, why there's something it's like to be a conscious being rather than just an abstract pattern. Another approach invokes a creator, a being or principle that brought the universe into existence. This doesn't necessarily mean a personal god as envisioned in religious traditions. It could be a more abstract principle, a necessary being whose existence requires no further explanation, and who or which gives rise to contingent beings like the universe. But this raises its own questions. Why does the creator exist? What explains the creator's properties and decisions? Some philosophers argue that the question is simply unanswerable. Why there is something rather than nothing might be a brute fact, a feature of reality that has no explanation. Not every question has an answer. Not every fact can be derived from deeper principles. At some point you reach bedrock, the fundamental features of existence that simply are, and the question of why they are has no answer. This might seem unsatisfying, but there's a certain honesty to it. Science and philosophy have limits. We can trace causation back, asking why for each phenomenon we encounter, but eventually we reach the end of the chain. Perhaps the existence of the universe is that endpoint. It exists, and that's all there is to say. Or perhaps the question contains a subtle mistake. Why is there something rather than nothing? Assumes that nothing is the default, the state that requires no explanation, and something is surprising. But maybe that assumption is wrong. Maybe something is the default and nothing would require explanation. If the quantum vacuum is the natural state, if all mathematical structures necessarily exist, if existence is inherently unstable and always produces universes, then asking why there's something is like asking why there are positive integers. They exist necessarily by definition, and the absence of them would be the real mystery. As we contemplate what came before the Big Bang, this foundational question lurks in the background. Whatever came before, whether it was another universe, a quantum vacuum, a timeless state, or something else entirely, we can always ask why that thing existed. And perhaps the answer is that existence itself is fundamental, requiring no cause or explanation, simply the way reality is, and always has been. Science has been extraordinarily successful at uncovering the workings of nature, from the smallest particles to the largest cosmic structures. But science has limits. There are questions it cannot answer. Not because we lack sufficient data or clever theories, but because the questions lie outside the domain where scientific methods apply. The question of what came before the Big Bang might be one of those questions, forever beyond the reach of empirical investigation. The fundamental challenge is observational. Science advances by making observations, forming hypotheses, testing predictions. But if what came before the Big Bang is causally disconnected from our universe, if no information from that earlier state can reach us, then we have no way to test hypotheses about it. Any theory becomes as good as any other, as long as it's logically consistent, because there's no observational evidence to distinguish between them. Consider the cosmic microwave background, the earliest light we can observe. It was emitted when the universe was 380,000 years old. Before that, the universe was opaque to light. We can't see earlier directly. We can infer what the universe was like by running the equations backward, but those inferences depend on assumptions about the laws of physics. If the laws were different before the Big Bang, or if quantum effects dominated in ways we don't understand, our inferences might be wrong. Some physicists argue that we can still make progress by relying on mathematical consistency and explanatory power. Even if we can't observe what came before the Big Bang, we can evaluate theories based on how well they explain the features we do observe. A theory that naturally produces the low-entropy initial state of the Big Bang is better than one that requires it as an unexplained assumption. A theory that unifies multiple phenomena is better than one that treats them separately. This is how much of theoretical physics already works. String theory, for instance, makes few testable predictions with current technology, but it's taken seriously because it offers a unified framework for all forces and particles, something no other theory achieves. Similarly, theories about what came before the Big Bang might be evaluated not by direct test, but by their elegance, simplicity, and ability to explain diverse observations. But there's a danger here. Without empirical constraints, theorists can construct elaborate mathematical edifices that have no connection to reality. History is full of beautiful theories that turned out to be wrong. The planets don't move in perfect circles despite the aesthetic appeal of circular orbits. The universe doesn't have a steady state despite the philosophical appeal of an eternal, unchanging cosmos. Beauty and elegance are guides, but they're not guarantees of truth. Some philosophers argue that the question of what came before the Big Bang is metaphysical, not scientific. Metaphysics deals with questions about the fundamental nature of reality, questions that can't be answered by observation alone. Science can tell us how the universe behaves, but metaphysics asks why it exists, what it's made of at the deepest level, what came first. These questions require reasoning and argument, not experiments and data. This doesn't mean metaphysics is useless or unrigorous. Philosophers have developed sophisticated methods for analysing concepts, identifying logical implications and evaluating arguments. But metaphysical conclusions don't have the same status as scientific theories. They're not subject to empirical testing in the same way. They're exercises in reasoning about what must be true given certain assumptions, not descriptions of what is true based on observation. Another limit on scientific knowing comes from the nature of mathematics itself. Gödel's incompleteness theorems show that any sufficiently complex mathematical system contains true statements that can't be proved within the system. If the universe is fundamentally mathematical, as some physicists believe, then there might be true facts about the universe that can't be derived from any set of axioms or observations. What came before the Big Bang might be one of those facts, true but unprovable, knowable only through some means beyond science. There's also the possibility of unknowable unknowns, facts about reality that we can't even conceive of asking about because they lie so far outside our experience and conceptual frameworks. Just as a dog can't understand calculus, not because it lacks intelligence, but because it lacks the conceptual tools, we might lack the tools to understand certain aspects of reality. What came before the Big Bang might involve dimensions, forces, or principles so alien to our experience that we literally can't formulate coherent questions about them. Despite these limits, the pursuit of knowledge is worthwhile. Even if we can't reach final, 90 minutes, you've been here for 90 minutes quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. Even if we can't reach final, certain answers about what came before the Big Bang, we can narrow the possibilities, rule out some scenarios, develop frameworks that make the question more precise. Science has a history of pushing beyond apparent limits. Questions once thought metaphysical have become scientific. The composition of stars, the age of Earth, the origin of species, all these were once beyond empirical investigation. Now they're settled science. Perhaps the same will happen with the question of what came before the Big Bang. Perhaps new technologies, new observations, new mathematical techniques will allow us to peer beyond the apparent boundary. Or perhaps the question will remain forever at the edge of the knowable, a mystery that reminds us that reality is deeper and stranger than our minds can fully grasp. There's a peculiar feature of quantum mechanics that some physicists and philosophers believe might be relevant to the question of what came before the Big Bang. It involves the role of observation in determining the state of quantum systems. In the standard interpretation, a quantum system exists in the superposition of states until it's measured. The act of measurement collapses the superposition into a definite state. But what counts as a measurement? And does observation require a conscious observer? Most physicists would say no. A measurement is any interaction that entangles the quantum system with a larger environment, causing the system to decohere and lose its quantum properties. Consciousness has nothing to do with it. A particle detector, a photographic plate, even a single atom can act as a measuring device. Consciousness is irrelevant to the physics. But some researchers, most famously physicist Eugene Wigner, have argued that consciousness might play a fundamental role. If a measuring device is itself a quantum system, as everything ultimately is, then it too exists in a superposition until measured. You can push the problem back. imagining larger and larger systems, but eventually you reach a conscious observer who perceives a definite outcome. At that point, the superposition collapses. In this view, consciousness is what makes quantum mechanics work, what transforms potentiality into actuality. If this is true, then the universe before conscious observers existed would have been in a state of superposition with no definite properties. Stars and galaxies would have existed in all possible configurations simultaneously. Only when life emerged and conscious beings observed the universe would it have collapsed into a definite state. This sounds absurd, but it's a logical consequence of taking the observer-dependent nature of quantum mechanics seriously. What does this have to do with what came before the Big Bang? If consciousness is necessary to collapse quantum superpositions, then the early universe, before any conscious observers existed, would have been in a state of maximal superposition. All possible configurations of matter and energy, all possible values of physical constants, all possible histories would have coexisted. The Big Bang, in this view, wouldn't have a definite starting configuration until conscious observers emerge billions of years later. This leads to a strange backward causation. The present state of the universe, containing conscious observers, reaches back in time and selects which configuration the early universe had. What came before the Big Bang wasn't a definite state. It was a superposition of all possible states, and our observation now determines which one actually occurred. The past is not fixed until it's observed, which means the Big Bang's properties are determined by the existence of observers in the present. This idea, sometimes called the participatory anthropic principle, was developed by physicist John Wheeler. He imagined the universe as a self-excited circuit, where observers play a role in bringing the universe into existence by observing it. It's not that consciousness creates the universe from nothing. It's that observation gives the universe definite properties, selecting one history from the many possible quantum histories. Most physicists find this too radical. They prefer interpretations of quantum mechanics that don't require consciousness, like the many worlds interpretation or decoherence theory. In many worlds, there's no collapse. All possible outcomes occur in different branches, and consciousness simply perceives one branch without affecting the others. In decoherence theory, interactions with the environment effectively collapse superpositions without any need for conscious observers. But the question of consciousness in quantum mechanics hasn't been settled. We still don't understand what consciousness is or how it arises from physical processes. We don't know if it's purely emergent, arising from complex information processing in brains, or if it's somehow fundamental, built into the fabric of reality. Some physicists, like Roger Penrose, have proposed that consciousness involves quantum processes in the brain, perhaps even quantum gravity effects that we don't yet understand. If consciousness is fundamental, then its role in the universe might be more profound than we realize. Perhaps what came before the Big Bang was a kind of proto-consciousness, a field or principle that contained the potential for awareness. The Big Bang could have been the moment when this proto-consciousness began to manifest in physical form, creating matter and energy as vehicles for its expression. This sounds more like mysticism than physics, but it's an idea that has been seriously considered by some thinkers at the intersection of science and philosophy. Another possibility is that consciousness and the universe co-arise. Neither exists independently. The universe creates conditions for consciousness to emerge, and consciousness, through observation, gives the universe definite properties. They're two aspects of a single, unified reality, neither prior to the other. In this view, asking what came before the Big Bang is like asking what came before the mutual arising of subject and object, observer and observed. The question assumes a separation that doesn't exist at the deepest level. These ideas are speculative, and they might turn out to be wrong. But they remind us that the question of what came before the Big Bang might be entangled with questions about consciousness, observation, and the nature of reality itself. The universe isn't just a mechanical system that existed before we came along to study it. We're part of the universe, and our role as observers might be more significant than we've acknowledged. When we ask what came before the Big Bang, and then ask what came before that, we might find ourselves in an infinite regress. Every answer prompts another question. The Big Bang came from a quantum fluctuation. What caused the quantum fluctuation? A previous universe in a cyclic model. What came before that universe? Another cycle. And before that, another cycle, ad infinitum. Some philosophers and theologians have argued that infinite regress is impossible, that there must be a first cause. An uncaused cause that started the chain. This is the cosmological argument for the existence of God, formulated by thinkers like Aristotle and Thomas Aquinas. If every event has a cause, and you can't have an infinite chain of causes stretching back forever, then there must be a first cause that itself requires no cause. This first cause is God, or a necessary being, or an ultimate principle. But is infinite regress really impossible? In mathematics, infinite sequences are perfectly coherent. The negative integers extend infinitely in one direction. The positive integers extend infinitely in the other. There's no first or last number. Each number has a predecessor and a successor, going on forever. If time is like the integers, extending infinitely into the past and future, then there's no first moment, no ultimate beginning. Some cosmological models embrace this possibility. In eternal inflation, the multiverse has no beginning. Bubble universes form constantly, each with its own Big Bang, but the inflating space between bubbles has always existed. In cyclic models, the universe bounces infinitely many times with no first cycle. In these models, the question, what came before, has an answer at every level. Before this Big Bang was the previous cycle. Before that was another cycle. There's always something earlier, infinitely far back. Critics argue that infinite regress leaves us without a satisfying explanation. If every event is explained by a previous event, you never reach a final explanation. You're left with an infinite chain where no link in the chain is self-explanatory. This feels incomplete, like you haven't really explained anything. Just push the mystery back infinitely. Proponents respond that this intuition is mistaken. An infinite chain doesn't need a final explanation if each link is explained by the previous link. The sequence as a whole doesn't require an external explanation. It's self-contained. Compare it to asking why there are infinitely many numbers. There's no external reason. It's just how the number system works. Each number is explained by the structure that includes all numbers. Another objection to infinite regress involves entropy. If the universe has been cycling infinitely, entropy should have increased with each cycle, eventually reaching a maximum where no more interesting structures can form. The fact that we exist in a relatively low entropy state suggests the universe hasn't been cycling forever. There must have been a beginning, or some mechanism that periodically resets entropy. Defenders of infinite regress argue that if the universe expands sufficiently between cycles, entropy density decreases even if total entropy increases. Or they propose that the cycles vary in such a way that entropy doesn't simply accumulate. Or they accept that we happen to exist relatively early in an infinite sequence, when entropy is still low enough for life. This requires invoking the anthropic principle, but it's not obviously impossible. There's also a mathematical argument involving actual versus potential infinities. Potential infinity is the idea that a sequence can continue without limit. You can always add one more number. But actual infinity is the idea that an infinite collection exists as a completed whole. Some philosophers argue that actual infinities are impossible, that you can't have an actually infinite collection of past events because you could never complete the journey from infinite past to the present. But this argument has been challenged. If time is infinite in both directions, there's no need to complete a journey from an infinite past. You just exist at a particular point in the sequence, with infinitely many events before and after. It's no more problematic than existing at a particular point on an infinite line. The question of whether infinite regress is possible might not be answerable by logic alone. It depends on what the actual structure of time and causation is, which is an empirical question about the nature of reality. If observation suggests the universe is cyclical, or part of an eternal multiverse, then infinite regress might be the correct description. Regardless of philosophical objections, what's interesting about infinite regress is that it transforms the question of what came before the Big Bang. Instead of looking for a single, ultimate answer, we accept that there's always something earlier. The question never ends. At every level there's a deeper level. This might seem frustrating, but it's also liberating. It means reality is inexhaustible, infinitely deep, always offering more to discover. And perhaps that's a more fitting picture of the cosmos than one with a tidy final explanation. There's something humbling about standing at the edge of knowledge, looking into the mystery of what came before the Big Bang and admitting we don't know. In a culture that values certainty and answers, that treats ignorance as weakness, it's tempting to grasp for explanations even when the evidence is thin. But there's wisdom in acknowledging limits, in saying this is what we know, and beyond that, we're uncertain. The history of science is full of premature certainties. For centuries, people were certain the Earth was the centre of the universe. They were certain time was absolute, the same for all observers. They were certain space and time were separate, independent entities. They were certain genes were made of protein, not DNA. They were certain the universe was static, neither expanding nor contracting. All of these certainties turned out to be wrong. The universe surprised us, revealing deeper structures than we imagined. Each time, the lesson was the same. Nature is subtle. Reality doesn't conform to our intuitions or our desires for simplicity. When we cling too tightly to our current understanding, we blind ourselves to possibilities we haven't yet conceived. The question of what came before the Big Bang is currently unanswered. We have multiple competing theories, each with strengths and weaknesses. We have observations that constrain but don't determine the answer. We have mathematical frameworks that offer different possibilities, but we don't have certainty. And maybe that's exactly where we should be at this stage of our understanding. Unanswered questions drive science forward. They motivate new observations, new experiments, new theoretical developments. If we already knew what came before the Big Bang, if the question were settled, then that entire avenue of research would close. Generations of physicists and cosmologists would lose a profound mystery to pursue. The fact that we don't know means there's still work to do, discoveries to make, insights to gain. There's also something aesthetically beautiful about mystery. A universe that's fully explained with no remaining questions would be less interesting than one with deep mysteries at its foundation. The fact that reality holds secrets, that there are questions we can ask but not yet answer, gives existence a kind of depth and richness. It means we live in a universe that's bigger than our understanding, that continues to surprise and challenge us. This doesn't mean we should abandon the pursuit of answers. The search for what came before the Big Bang is worthwhile, even if we never reach a final conclusion. The journey itself is valuable. As we explore this question, we develop new mathematical techniques, new observational methods, new ways of thinking about time and causation and existence. Even if we never determine whether the universe bounced or emerged from a quantum fluctuation, or is part of a multiverse, we'll have learned something profound about the structure of reality, and maybe the question is unanswerable in principle. Maybe the Big Bang represents a true boundary of knowledge, a horizon beyond which we can't see. If that's the case, then the appropriate response is not frustration but acceptance. There are limits to what we can know, and that's okay. We can still understand the universe from the Big Bang forward, tracing how galaxies formed, how stars ignited, how planets coalesced, how life emerged. That's an enormous, beautiful story, even if we can't access the prologue. Some mysteries might require new kinds of thinking, new frameworks that we haven't yet developed. Just as quantum mechanics required abandoning classical intuitions about particles and waves, understanding what came before the Big Bang might require abandoning intuitions about time, causation, or existence itself. We might need conceptual tools we don't yet have, ways of thinking that will seem as strange to us now as quantum superposition seemed to physicists in the early 20th century. The next generation of scientists and philosophers will approach this question with fresh perspectives, building on our work but not limited by our assumptions. They'll have better observations, more powerful mathematics, new insights from disciplines we haven't yet imagined, and perhaps they'll make progress that seems impossible to us now. Or perhaps they'll discover that the question is deeper and stranger than we realised, opening new layers of mystery beneath the current one. Either way, the question of what came before the Big Bang will continue to inspire wonder. It's one of the fundamental questions we can ask about existence, right up there with, why is there something rather than nothing, and what is consciousness? These aren't just scientific questions, they're philosophical, existential, spiritual questions that touch on the nature of reality itself. As we contemplate these mysteries, we're participating in a tradition that extends back to the earliest human cultures. People have always looked at the sky and wondered where it all came from. They've told stories of creation, imagined cosmic battles, proposed cycles of birth and death and rebirth. We're continuing that tradition, using the tools of modern science, but asking the same fundamental questions our ancestors asked around fires 10,000 years ago. And in that continuity, there's something deeply human and deeply beautiful. We're creatures who wonder, who ask questions, who seek understanding even when answers seem impossibly distant. The question of what came before the Big Bang might never be fully answered, but the asking, the exploring, the reaching toward the unknowable, that's what makes us human. And that's worth celebrating, even in the midst of uncertainty. When we reach the limits of knowledge, when our best theories become speculation, and our observations fail to provide definitive answers, there's a kind of silence that descends. It's not an absence of information, but a recognition that we've arrived at a boundary. Beyond this point, the universe doesn't speak clearly. It whispers in mathematics and hints in cosmic microwave background anomalies, but it doesn't declare certainties. This silence has something to teach us. In a world saturated with information, with constant streams of data and opinion and noise, the silence at the edge of the knowledge is refreshing. It reminds us that not everything can be known immediately, that some questions require patience and humility. The universe isn't obligated to make sense to us on our timescale. It's been here for 13.8 billion years. It can wait for us to develop the tools and concepts we need. There's a difference between ignorance born of laziness and ignorance born of reaching the frontier. When we say we don't know what came before the Big Bang, we're not admitting defeat. We're acknowledging that we've explored as far as current methods allow. We've considered quantum fluctuations and cyclic universes and eternal inflation and black hole bounces. We've done the mathematics, made the observations, constructed the theories, and we've found that multiple possibilities remain open, none definitively confirmed or ruled out. This kind of ignorance is productive. It's the ignorance that motivates research, that drives scientists to build better telescopes and develop more sophisticated mathematical frameworks. It's the ignorance that admits what it doesn't know, while continuing to push forward, trying new approaches, testing new ideas. It's an active, engaged ignorance, very different from the passive acceptance of not knowing. The silence also teaches humility. For all our technological advancement, for all our scientific achievements, we're still confronted by questions we can't answer. The universe is bigger and older and stranger than we are. It contains mysteries that might outlast our species. And there's something right about that. If we could explain everything, if every mystery dissolved under scrutiny, the universe would be diminished. It would be less than it appears, reducible to equations and mechanisms. But the universe resists total explanation. Even our best theories have gaps. Even our most complete descriptions leave questions unanswered, and maybe that's how it should be. Maybe mystery is a fundamental feature of existence, not a temporary state of ignorance that will eventually be dispelled. Maybe some questions, including what came before the Big Bang, will always reside at the boundary between known and unknown, illuminated enough to ask coherent questions but not enough to provide certain answers. This doesn't mean we should embrace mysticism or abandon reason. The silence at the edge of knowledge isn't a license to fill the gaps with whatever appeals to us emotionally or spiritually. It's a reminder to be careful, to distinguish what we know from what we speculate, to hold our theories lightly while remaining committed to evidence and logic. There's a philosophical tradition, going back at least to Socrates, that wisdom begins with recognizing what you don't know. The Socratic insight was that most people think they know things they don't, and this false knowledge prevents them from seeking truth. By admitting ignorance, you open yourself to learning. You become curious rather than complacent, questioning rather than certain. In cosmology, this means recognizing that what came before the Big Bang is currently unknown. We have ideas, some more promising than others, but we don't have certainty, and that's okay. It's not a failure. It's the current state of our understanding, and it's a state that invites further exploration. The silence also invites contemplation. When you reach the edge of what can be said scientifically, you enter territory where philosophy and poetry and even spirituality have something to offer. Not as substitutes for science, but as different ways of engaging with mystery. Science seeks explanations. But sometimes the deepest questions are less about explanation and more about meaning. What does it mean that the universe had a beginning? What does it mean that something came before, or that time itself might have emerged from timelessness? These questions don't have scientific answers, but they're still worth asking. They connect the cosmological mystery to the existential mystery of being alive, of being conscious, of finding ourselves in a universe we didn't create and can't fully understand. The silence at the edge of knowledge is where these different modes of inquiry meet, where science and philosophy and spirituality recognize their shared limitations and perhaps their shared wonder. And in that silence, if we're quiet enough, we might hear something. Not an answer exactly, but a resonance. The universe doesn't explain itself in words, but it shows itself in patterns. The cosmic microwave background, the distribution of galaxies, the mathematical elegance of physical laws, these are the universe speaking in its own language. And learning to listen, learning to be comfortable with partial understanding and open questions, that might be the most important lesson the silence has to teach. It's easy to feel small when contemplating questions about what came before the Big Bang. The scales involved are incomprehensible. 13.8 billion years, hundreds of billions of galaxies, possibly infinite universes in a multiverse. Against this vastness, a single human life, spanning a few decades on one planet orbiting an ordinary star, seems insignificant. But there's another way to think about it. We are the universe's way of knowing itself. Somewhere in this vast cosmos, on at least one planet orbiting at least one star, matter organized itself into structures complex enough to wonder about their own origins. Atoms that formed in the cores of ancient stars came together to create brains capable of asking where the Big Bang came from. That's not insignificant. That's remarkable. The fact that we can even formulate the question of what came before the Big Bang is extraordinary. It requires language, abstract thought, mathematics, the ability to imagine states of reality radically different from our everyday experience. It requires cultures that value inquiry, institutions that support scientific research, technologies that allow us to peer back in time by observing distant light. All of that arose through a chain of events that began with the Big Bang, or with whatever came before it. The laws of physics allowed hydrogen and helium to form. Gravity caused those elements to clump into galaxies and stars. Nuclear fusion in stellar cores created heavier elements. Supernovae scattered those elements into space. New stars formed with rocky planets. On at least one planet, chemistry became biology. Single-celled organisms became multicellular. Life became more complex, more aware, until eventually there were beings capable of looking back at the process that created them and asking how it began. This doesn't mean we're the purpose of the universe. The universe doesn't need a purpose. It simply is. But it does mean we're connected to the cosmic story in a profound way. The same processes that formed galaxies also formed us. The same laws that govern black holes govern the neurons in our brains. We're not separate from the cosmos, observing it from outside. We're part of it, expressions of it, the universe experiencing itself. When we ask what came before the Big Bang, we're participating in the universe's ongoing self-discovery. Each generation asks the question with new tools, new insights, new perspectives. Our ancestors looked at the night sky and saw gods and heroes. We look at the same sky and see the cosmic microwave background, the afterglow of the Big Bang. Future generations will look and see things we can't yet imagine. The question evolves as our understanding evolves, but the impulse to ask remains constant. There's something deeply human about this impulse. We're not content to simply exist. We want to know why we exist, where we came from, where we're going. These questions might not have survival value in the immediate sense. Knowing what came before the Big Bang doesn't help you find food or avoid predators, but it satisfies something deeper, a need for meaning and connection, a desire to understand our place in the larger scheme of things. Different cultures have approached these questions differently. Some told mythological stories of creation, gods shaping the world from chaos or nothingness. Some developed philosophical systems exploring the nature of being and becoming. Some turned to science, using observation and reason to trace the universe's history. All these approaches reflect the same fundamental human need to make sense of existence. What's powerful about the scientific approach is its humility and its honesty. When we say we don't know what came before the Big Bang, we're not saying the question is meaningless or unanswerable. We're saying we haven't found the answer yet. We're admitting the limits of our current understanding while remaining open to future discoveries. This is a mature, thoughtful way of engaging with mystery, very different from either dogmatic certainty or nihilistic dismissal. And the search itself is meaningful, even if we never reach final answers. The process of asking, investigating, theorizing, observing, refining our understanding, this process enriches human culture. It creates knowledge that future generations can build on. It develops technologies that have applications beyond cosmology. It trains minds to think rigorously and creatively. It inspires wonder and humility. When you look at images from the James Webb Space Telescope, showing galaxies as they appeared billions of years ago, you're seeing the universe revealing itself. When you read about theories of eternal inflation or bouncing cosmologies, you're seeing human minds grappling with the deepest questions we can ask. When you contemplate the possibility that our universe emerged from a quantum fluctuation, or a black hole in a parent universe, you're stretching your imagination to encompass realities beyond everyday experience. All of this is significant. It's what makes human life rich and meaningful, what elevates us beyond mere survival. We're creatures who wonder, who question, who reach toward the infinite even knowing we might never grasp it. And that reaching, that striving for understanding, is as much a part of the cosmic story as the formation of stars or the expansion of space. So when you feel small contemplating the vastness of cosmic time and space, remember that you're part of that vastness. The atoms in your body were forged in stars. The thoughts in your mind are emergent properties of the laws of physics. The questions you ask about the universe are the universe asking questions about itself. You're not insignificant. You're the cosmos made conscious, gazing back at its own origins with wonder and curiosity and awe. One of the challenges of contemplating what came before the Big Bang is that the possible answers are incomprehensible in a deep sense. Not incomprehensible because we lack the intelligence to understand them, but because they involve concepts that don't fit into our ordinary experience of reality. Timeless states, infinite regress, quantum superpositions of entire universes, dimensions beyond the three we perceive. These aren't just difficult ideas. They're ideas that challenge the very categories we use to make sense of the world. We evolved to navigate a world of medium-sized objects moving at moderate speeds. Our brains are wired to understand rocks and trees and other people, not quantum fluctuations or curved space-time. When physics reveals that the universe operates according to principles very different from our everyday intuitions, we struggle to make sense of it. We can do the mathematics, we can make predictions and test them, but truly grasping what the mathematics describes, forming a mental picture of it, that's often impossible. This is where metaphor and analogy become important. Scientists use them constantly when explaining complex ideas. The Big Bang is like an explosion, except it's not an explosion. Space is like a fabric, except it's not a fabric. Particles are like tiny billiard balls, except they're also like waves, and really they're neither. These metaphors help, but they also mislead. They give us something to hold on to, but they can't capture the full reality. Perhaps the right response to this incomprehensibility is not frustration, but acceptance. The universe doesn't owe us comprehensibility. It is what it is, and we do our best to understand it with the tools we have. Sometimes those tools are adequate. We can understand how planets orbit stars, how DNA encodes proteins, how electricity flows through circuits, but sometimes the tools fail. We can describe what happens mathematically, but we can't visualize it or make it intuitive. There's a kind of peace in accepting this. It means letting go of the expectation that everything should make sense in familiar terms. It means being comfortable with abstraction, with descriptions that are accurate without being visualizable. It means trusting the mathematics even when it leads to conclusions that seem paradoxical or impossible. This acceptance is not resignation. It's a mature recognition of how knowledge works. We understand the world through models and frameworks, and those models are always incomplete, always approximations. Newtonian physics is a model that works beautifully for everyday objects, but breaks down at very high speeds or very strong gravity fields. Quantum mechanics is a model that works beautifully for atoms and particles, but is hard to reconcile with general relativity. Every model has limits, and at those limits, our understanding becomes fuzzy. What came before the Big Bang is firmly in that fuzzy region. We're trying to describe a state or event at the absolute boundary of the observable universe, where quantum mechanics and general relativity both become essential, but haven't been unified. We're extrapolating beyond where our theories have been tested. The answers we propose are necessarily speculative, based on principles we think are correct but can't verify in these extreme conditions. And yet, even in this incomprehensibility, there are patterns and insights. We know the universe is governed by mathematical laws. We know those laws are elegant and consistent. We know that seemingly disparate phenomena often turn out to be connected. These regularities give us confidence that reality, however strange, has a structure we can gradually uncover. The incomprehensibility also reminds us of the value of different ways of knowing. Science gives us precise, testable descriptions of how things work. But philosophy gives us frameworks for thinking about meaning and existence. Art gives us ways to express the emotional and aesthetic dimensions of reality. Spirituality gives us practices for engaging with mystery and transcendence. None of these replace science, but they complement it, offering different lenses through which to view the same underlying reality. When contemplating what came before the Big Bang, it might help to draw on all these ways of knowing. Use the science to understand the physics, the mathematics, the observational evidence. Use philosophy to think about causation, time, and existence. Use art to explore the aesthetic and emotional responses the question evokes. Use spirituality if it resonates. to find meaning and connection in the vastness of cosmic time and space. The incomprehensibility of cosmic origins can actually be a source of wonder rather than frustration. It means the universe is deeper than our minds, richer than our theories, more mysterious than our explanations. There's always more to discover, more to understand, more to contemplate, and that inexhaustibility is, in its own way, beautiful. It also means we should approach these questions with intellectual humility. We don't have all the answers. We might never have all the answers, and that's okay. The universe has been here for billions of years before we arrived, and it will likely be here for trillions of years after we're gone. It's not waiting for us to understand it. It's simply unfolding according to its nature, and we're fortunate to be part of it, to observe it, to ask questions about it, even when those questions lead to incomprehensible answers. As we near the end of our journey through the question of what came before the Big Bang, it's worth considering a radically different perspective on time itself. What if the past and future aren't fundamentally different from the present? What if all of time, past, present, and future exists simultaneously in some deeper sense? This is the block universe view, and it has profound implications for how we think about the Big Bang and what came before. In our everyday experience, time flows. The past is gone. The future hasn't happened yet, and only the present exists. But Einstein's relativity challenges this picture. In relativity, different observers can disagree about whether two events are simultaneous. What's happening? Quote 14 for you might be in the past or future for someone moving at a different velocity. This suggests that quote 15 isn't a universal feature of reality, but a perspective-dependent phenomenon. If that's true, then the flowing river of time might be an illusion. The deeper reality might be a four-dimensional space-time where past, present and future all exist on equal footing. Just as all points in space exist simultaneously, even though you can only be at one point at a time, all moments in time might exist simultaneously, even though you can only experience one moment at a time. In this block universe view, the Big Bang isn't an event that happened in the past. It's a region of space-time that exists, along with all subsequent moments, in an eternal present. When we ask what came before the Big Bang, we're asking about a region of space-time that might or might not exist, depending on the structure of the block. If time has a boundary at the Big Bang, then there's no quote 16 region. If time extends infinitely or loops back on itself, then there are other regions, but they all exist together in the four-dimensional space-time structure. This perspective dissolves some of the puzzles about causation and origin. We're used to thinking causally, with earlier events causing later events. But in a block universe, causation might be better understood as a pattern of correlations within the four-dimensional structure. The Big Bang doesn't cause later events in time. Rather, there's a pattern where regions of space-time near the Big Bang have certain properties, and regions farther away have properties that are correlated with them in ways we describe mathematically. What came before the Big Bang in this view isn't a temporal question at all. It's a question about the geometry of the space-time block. Does the block have a boundary at the Big Bang, or does it extend further? If it extends further, what does that extended region look like? These are questions about structure, not about temporal sequence. Some people find the block universe view disturbing because it seems to eliminate free will and make the future fixed. If all moments exist equally, then the future is already determined, already part of the eternal structure. But defenders of the block universe argue that this doesn't eliminate free will in any meaningful sense. Your choices are still your choices, made based on your desires and reasoning. The fact that those choices are part of the four-dimensional structure doesn't make them any less yours. There's also something peaceful about the block universe view. It means that everything that has ever existed or will ever exist is preserved in the space-time structure. Nothing is truly lost. The past isn't gone. It still exists in its region of space-time. Loved ones who have died still exist in the moments we shared with them. Those moments are just as real as this present moment, even though we can't access them from here. Applied to cosmology, The block universe view suggests that what came before the Big Bang is a question about the complete structure of space-time, not about temporal priority. If the universe is eternal, with cycles or branches extending infinitely in both temporal directions, then the block is infinite, containing all those cycles or branches. If the universe began with the Big Bang, then the block has a boundary there, and there's no before in the temporal sense, just as there's no underscore quote underscore 18 underscore in the spatial sense. This might seem like a semantic distinction, but it's actually profound. It shifts the question from what happened before to what is the complete structure of space-time, and that's a question that might have a clearer answer. We can investigate the geometry of space-time using mathematics and observations. We can ask whether it's finite or infinite, whether it has boundaries or extends eternally, whether it branches or loops. The block universe view also connects to the idea that the present moment is all we truly have. Even if past and future exist in some four-dimensional sense, you only experience the present. Right now, reading these words or listening to this voice, this is your moment of existence. The past is memory, the future is anticipation, but the reality of your experience is here, now, in this eternal present that is the only time you ever actually inhabit. This brings us to a meditative perspective. Instead of worrying about what came before the Big Bang or what will happen in the distant future, we can rest in the present moment, the only moment that's directly accessible. The mysteries of cosmic origin are fascinating to contemplate, but they don't change the reality of being here, now, aware and alive. And perhaps that presence, that awareness of the present moment, is more fundamental than any question about temporal sequence or cosmic origins. We've travelled through theories and possibilities, mathematics and philosophy, from quantum fluctuations to cyclic universes, from black holes giving birth to new cosmos to holographic principles and simulations. We've explored the scientific frontiers and the philosophical depths. And now, approaching the end of our journey, we can ask, what are we left with? Not certainty. We don't know what came before the Big Bang, if quote 21 even makes sense. We have candidates, possibilities, frameworks that are more or less plausible, more or less supported by evidence. But we don't have a final answer, and we might not have one for a long time, perhaps ever. We're left with questions that remain open, mysteries that persist despite our best efforts. This is humbling, but it's also appropriate. The universe is under no obligation to reveal its deepest secrets on our schedule. We've only been doing serious cosmology for about a century. In the cosmic timescale, that's nothing. We're at the very beginning of our exploration, and it's natural that profound questions remain unanswered. We're left with a sense of wonder. The fact that we can even ask about what came before the Big Bang, that we can formulate coherent theories and make testable predictions, is extraordinary. A few centuries ago, such questions were purely metaphysical, beyond the reach of science. Now they're on the boundary, part scientific, part philosophical, but approachable with the tools of reason and observation. We're left with multiple possibilities, each with its own appeal. Perhaps the universe bounced from a previous contracting phase. Perhaps it emerged from a quantum fluctuation in an eternal vacuum. Perhaps it's one bubble in an infinite multiverse. Perhaps it formed in a black hole in a parent universe. Perhaps time itself emerged at the Big Bang, making before meaningless. Each of these possibilities expands our imagination, challenges our assumptions, reveals new aspect of what reality might be. We're left with the recognition that some questions might be unanswerable, not because they're meaningless, but because they're beyond the reach of observation and experiment. If what came before the Big Bang is causally disconnected from our universe, if no information from that state can reach us, then we might never know for certain. We can theorize, model, and explore, but definitive answers might remain elusive. And yet, we're left with progress. Our understanding of the early universe has advanced remarkably over the past century. We've measured the cosmic microwave background, mapped the distribution of galaxies, detected gravitational waves, and developed sophisticated mathematical frameworks for describing extreme conditions. Each discovery narrows the possibilities, constrains the theories, brings us closer to understanding even if we haven't arrived. We're left with a deeper appreciation for the nature of scientific inquiry. Science doesn't always provide clear, final answers. Sometimes it provides probabilities, ranges of possibilities, best current estimates. It's a process of gradually refining understanding, not a destination of absolute certainty. And that's okay. It's how knowledge grows, how we approach truth even when we can't grasp it fully. We're left with connections to larger philosophical and spiritual questions. What came before the Big Bang touches on existence, meaning purpose, the nature of time and causation. These aren't just scientific questions. They're human questions. Questions about our place in the cosmos, our relationship to the infinite, our capacity to understand and wonder. We're left with a sense of our own smallness and significance. Small because we're tiny beings on a tiny planet in a vast universe that might be one among countless others. Significant because we're the part of the universe that can reflect on itself, that can ask where it came from and why it exists. This paradox, being simultaneously insignificant and central, is part of what makes the contemplation of cosmic origin so compelling. We're left with a narrative, a story that connects the Big Bang to this moment. Whatever came before, the Big Bang began a chain of events that led to atoms, molecules, stars, galaxies, planets, and eventually life and consciousness. We're part of that chain. Our existence is a consequence of the conditions set in motion at or before the Big Bang. Understanding those conditions is understanding our own origins at the deepest level. We're left with hope for future discoveries. New telescopes will probe further into the cosmic microwave background. New detectors will search for gravitational waves from the early universe. New theories will emerge, combining quantum mechanics and general relativity in ways we haven't yet imagined. The question of what came before the Big Bang will continue to be explored, refined, deepened, and we're left with peace. Peace in acknowledging what we don't know. Peace in accepting the limits of current understanding while remaining curious and engaged. Peace in recognizing that the universe is vast and mysterious and beautiful, and that our exploration of it is meaningful even when it doesn't reach final conclusions. This peace doesn't come from having all the answers. It comes from asking good questions, from pursuing understanding with rigor and honesty, from remaining open to wonder. It comes from recognizing that we're part of something much larger than ourselves, something that existed long before we did, and will exist long after we're gone, and that our brief moment of awareness is a precious gift, an opportunity to contemplate the cosmos and our place within it. And so we come to the end of our journey together through the mystery of what came before the Big Bang. Thank you for staying with me for these 2.5 hours, for bringing your curiosity and your patience, for being willing to sit with uncertainty and explore the edges of human knowledge. It's no small thing to spend time contemplating questions that have no clear answers, and I'm grateful you chose to do so tonight. We've travelled from the moment we once thought was the beginning, through quantum fluctuations and cyclic universes, past black holes and multiverses, into the philosophical depths of existence and time. From the concrete observations of the cosmic microwave background to the abstract mathematics of eternal inflation, from the incomprehensible to the barely graspable, we have explored what might lie beyond the boundary of the Big Bang. And what have we found? We've found that the question _quote_23_ might have many answers, or no answer, or an answer we can't yet formulate. We found that the universe is stranger and richer than our everyday experience suggests, that reality operates according to principles that challenge our intuitions and expand our imaginations. We've found that science and philosophy intertwine at the deepest questions, that knowledge has limits, but those limits are worth exploring. Perhaps the most honest answer I can give. Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. Perhaps the most honest answer I can give you is this. We don't know what came before the Big Bang, but we're learning how to ask the question better. We're developing the tools, the theories, the observations that might one day give us an answer. Or perhaps we'll discover that the question itself needs to be reformulated, that before doesn't apply, that time and causation are more subtle than we realized. Either way, the exploration is worthwhile. The journey matters, even when the destination remains distant. If you found this slow drift through cosmic mysteries helpful, if it gave you something to contemplate or learn, a like and subscribe would help others find their way to these calm explorations. And if you have thoughts, questions, or insights that this journey sparked, I'd love to hear them in the comments. This community of curious minds is part of what makes creating these videos meaningful. To those who've been with me before, who return again and again to these long contemplative journeys, thank you. Your presence here matters more than you know, wherever you are in the world right now. Whatever time of night or day you're experiencing this, I hope you're comfortable. I hope your breathing has slowed, that your thoughts have quieted, that the day's worries have receded. I hope your body feels heavy and warm, ready for rest. This journey through cosmic time has reached its end, and it's time to let it settle, to let the vastness and the mystery simply be. Look up at the night sky, if you can, or imagine it in your mind. Those stars, those distant points of light, are suns like ours, some younger, some older, some already gone, their light still reaching us across the years. Between them stretches the dark, and in that dark the cosmic microwave background whispers of the Big Bang. Of the moment everything we can see began its expansion, and beyond that, perhaps other universes, perhaps earlier cycles, perhaps a quantum foam from which all things emerge, perhaps something we haven't imagined yet, perhaps nothing at all. The answer, whatever it is, doesn't change the beauty of this moment. You exist. You're aware. You've spent these hours contemplating the deepest mysteries we can ask about existence. That's a profound way to end a day, to transition from waking to sleeping, from the particular concerns of your life to the universal questions that connect us all. In the end, what we're left with is not certainty but wonder, not answers but better questions, not a complete picture but a glimpse of patterns too vast to fully comprehend. And that's enough. It has to be enough, because it's what we have, and it's beautiful. Sleep well tonight. Dream of quantum fluctuations giving birth to universes, of time flowing in both directions from a single moment, of infinite cycles of expansion and contraction, of mysteries that persist despite our best efforts to solve them. Dream of the cosmic microwave background, that ancient light carrying whispers of the beginning. Dream of the question we've explored together, turning it over in your sleeping mind, letting it become part of the vast landscape of things you've wondered about. And know that tomorrow, when you wake, the question will still be there, waiting for new minds, new observations, new insights. The universe will still be expanding, still holding its secrets, still inviting us to look deeper, to ask harder questions, to reach for understanding even when it seems impossibly distant. Good night. Rest in the mystery. Let the unknowable cradle you as you drift towards sleep. and thank you truly for travelling with me through this long contemplative exploration of what might have come before the beginning. May your sleep be deep, your dreams be peaceful, and your tomorrow be filled with the same wonder and curiosity that brought you here tonight. Good night.